What I'd like you to do is read example 9, checking for extraneous solutions. And we know that in quadratic functions, oftentimes we can have imaginary solutions. And so we want to check the values that we get when we solve back in the original equation. I want you to read example 9 and then try problem 109, and we'll come right back here and check your solutions. So here you can see we have problem 109 written out. On the right hand side we can use some of our properties of condensing logs. We understand that subtraction simply is division, so we're going to take the first term, x minus 1, divided by, subtraction is just repeated, let me back up, division is repeated subtraction, so those two are related and it should make sense as to why. And on the left hand side we have the log x plus 5. Well, in the previous example we used exponentiation, so if I raise each side as a power of e to the log e, that just leaves us with the algebraic expressions x plus 5 equaling x minus 1 over x plus 1. And what we see now is simple algebraic problem solving. We're going to multiply both sides by x plus 1. And we're going to solve. We're going to subtract the x minus 1 right off the bat and get it set equal to 0. So in performing the multiplication in the first part of this, we get x squared plus 6x plus 5, and we're going to subtract x and add 1, leaving us with x squared plus 5x plus 6, and we can see that that factors into x plus 3, x plus 2. Solving for those equal to 0, we see x is equal to negative 3 or negative 2. And this is where, of course, we want to check for extraneous solutions. So substituting both of these back into the original, we get natural log. Let's go with the negative 3 first. Negative 3 plus 5 is equal to the natural log of negative 3 minus 1 minus the natural log of negative 3 plus 1. Natural log of 2, is that equal to the natural log of negative 4 minus 1, back up. Natural log of negative 4 minus the natural log of negative 2. So we can see right off the bat, we can take the natural log 2. It's saying e to what power is 2? The base 2.718 2 point ... to some power is 2 something. Well, that makes sense. But if we look on the right hand side of the equation in this first part, we're saying e to what power is negative 4, followed by e to what power is negative 2. And we know if we take that positive base e, there's no power that will lead us to a negative solution. So we have two extraneous values. We can see plugging in negative 3 yields negatives on the right hand side. Negative 2 in this first case, negative 2 minus 1 would give us the natural log of negative 3. Negative 2 plus 1 would give us the natural log of negative 1. So both negative 3 and negative 2 are extraneous solutions, and we have further investigation to do. So after reading example example 12, they were wondering when we could double an investment, which is always a really intriguing thought. We want to invest money and have it come out twice as fluffy as when we sent it into the bank. You guys were reconsidering this concept of compounding continuously. And I want you to recall that we are using that equation, the amount left in after a principal amount was invested is equal to the principal times e to the RT. So the first thing we're looking at is wanting to double this amount, the amount left after the investment. So the double of 1,000 would give us 2,000. The original principal was 1,000, and we know E is our constant. Our rate, 7.5, if we turn that into our decimal 0.075, and we're solving for the time it takes. That's what we want to do. So we've been working with these algebraically. We know we're going to divide both sides by 1,000, and we get 2, which makes sense. We're doubling. And how are we solving this type of problem? How did we get rid of the constant e to be left with the exponential algebraic exponent? You're right. We're going to take the natural log of both sides. Natural log of 2 is equal to, remember these are inverses of each other and they cancel, and we get 0.075 t. Dividing both sides by that rate, we can see natural log 0.075, and quick calculation, the log of 2 divided by 0.075 yields time 9.24 years. Well, if it's $1,000 you can just stick in the bank and forget about. That's a pretty good deal. In 9 years you've doubled. The next part of the question, of course, asks how long to triple. So instead of 2,000 equaling 1,000 e to the RT, we're going to have 3,000 equals 1,000 e to the RT. You'll work this the exact same way. We just have a new value, 3. 3 is equal to e to the 0.075 t. We're going to take the natural log of both sides, and natural log of 3 divided by 0.075 yields approximately 14.65 years. We're solving for t, so both of these are in years.